Hello, hello. I am Mrs. Edwards, and it is time to do math, and I love it. Today we're going to be doing some exponential functions, but first I have a story for you. You're sitting in math class, minding your own business, when in walks this Bill Gates sort of guy, the real success of your school. He's made it big, but now he has a job offer for you. He doesn't give too many details, mumbles something about danger, and he says he's going to need you for 30 days and you might need to miss school. Oh man, might that be awful. And you've got to make sure your passport is current. Get real, Bill, come on, travel. But do you ever sit up and take notice at the next thing he says? He says you'll have two payment options. One payment option will be $1 million. Or you can have 1 cent on the first day, 2 cents on the second day, doubling your salary every day for each of those 30 days. $1 million? You jump up out of your seat and you're like, Bill, right here. I'll take it. I'm your man. And off you go on your dangerous mission. But did you select the best option for your salary? So you could have $1 million, or you could have a penny your first day, double it. 2 pennies day 2, double it. 4 cents your next day. By the time you get to day 7, you're up to a whopping 64 cents, making your total salary by the end of day 7, after that first week, $1.27. Oh, this is some excitement. Well, let's keep looking. Day 8, you're being paid $1.28. Double your salary, double your salary, double. We're up to $10.24. We might be over minimum wage. Well, wait, maybe not. Okay, then we're to, on day 12, $20.48, doubling it. And by day 14, on that day, you get paid $81.92. And if we add up all the money you've made so far in those 14 days, you're up to $163.83. Well, you're nearly halfway done with the job, and you've only been paid $163.83 compared to that $1 million. Well, let's keep looking. Okay, day 15, $163, double your salary, double it. Well, by day 21, on day 21, you're being paid over $10,000, and after 3 weeks, you would have made almost $21,000, which frankly still doesn't seem like very much compared to that $1 million. Let's keep looking. Currently, you're being paid just over $10,000. Okay, doubling it, we're over $20,000. Double. Ooh, double. Holy cow, double. By day 28, you are making over $1 million, bringing your grand total of how much money you've made in the job to over $2.5 million. But you get to work for 30 days. So if day 28, you're making over $1 million, well, day 29, you're making over $2 million, and day 30, just for day 30, you are getting paid over $5 million. Okay, so then if you add up all of your week's pays, you would have earned nearly $11 million. This is a fantastic example of exponential growth. Exponential growth, if you've had a savings account and you've got your money in there and you get interest on your money and you're like, ooh, let me see what I made this month. Oh yes, 3 cents if you're lucky. And you're like, what's the big deal about saving money? Well, it's about exponential growth. You put your money even to a savings account, making 1%, maybe 2% if you're lucky. But if you put your money in long-term, like into mutual funds or something, this is how your money is growing in those investments. It doesn't look like much. Think about this like as year 30. We could be 15 years in, right, halfway there to retirement, and it doesn't really look like much is going on. But In those later years, exponential growth, at first, it doesn't look like it's growing very much, but then it really takes off and skyrockets. So super exciting stuff. Well, let's take a look at some exponential functions. Here we've got our first exponential function that we're going to graph, y equals 2 to the x. Now notice the location of x. X is sitting there in the exponent spot. When that variable is in the exponent, that is a giveaway that you're probably looking at an exponential function. Okay, now we'd like to graph, and we don't have a parent function at this point. We can't use shifts just yet, those transformations. So the fallback plan when you don't know what a graph looks like is just plot a whole bunch of points until you get a gist of what is happening. So let's begin by substituting in 0. 2 to the 0 power. Anything to the 0 power equals 1. So there's our y-intercept, because you find a y-intercept by letting x be 0. Okay, I substitute 1. 2 to the first power is 2. 2 to the second power is 4. 2 to the third power, 2 times 2 is 4 times 2 is 8. Okay, so we get 8 there. We plotted our point. Now notice this one, it's like we started with $1 and then we doubled it 2, doubled it 4, doubled it 8. At 4, we'd be doubling it 16. By the time we get to 5, substitute that in. 2 to the 5th power is 32. Plot a point. Plug in 9. 2 to the 9th power is 512. Okay, then I substitute 20, and we're already over 1 million. So notice how this is skyrocketing, right? The larger and larger x value I select, the y value is getting bigger and bigger, and it gets big really, really fast. Exponential functions grow very, very quickly. How about on the other side? I substitute in -1. Okay, when I plug in -1, I get 2 to the -1, and an exponent that's negative, we cross the fraction bar line to change the sign of the exponent. I call that cross the line to change the sign. And then we have 1/2, so I plot that point. Okay, maybe I plug in -3. And we have 2 to the -3, cross the fraction bar line to change the sign on the exponent. And 2 times 2 times 2 is 8. Plot the point. -3 1/8. Now notice what's going to happen here. Even if I plug in -17, we're going to end up with a positive answer because it would be 1 over 2 to the +17. And 1 divided by an enormous positive number is a teeny tiny answer. So the answers, as I start substituting in numbers going to the left, they're going to get smaller and smaller and smaller. They're never going to become negative, and they're not going to become 0. So the overall look of this graph looks like that. And because it's getting closer and closer to the x-axis, we have a horizontal asymptote that is the x-axis. The equation for that, of course, is y equals 0. Okay, these are some features of exponential functions. We have a horizontal asymptote there that's the x-axis, and it contains the point 0, 1. Now, these curves are sometimes referred to as the J curve. Okay, and that name's not bad. It kind of helps us remember in general what they look like. But the only thing you have to be careful of when you hear the J curve is the letter in the alphabet J. It comes down, right, looks like this, but then it starts coming back up. Okay, it's not going to come up. It's going to draw nearer and nearer and nearer this horizontal asymptote. So when we call them a J curve, just remember they're not coming back up and then creating a parabola. They're just going to keep on getting closer and closer to a horizontal line. And in this case, that is y equals 0. Okay, the domain, this function, it goes forever to the left and it goes forever to the right. Right? I can substitute in any number I want in for x, and I'm going to get out a real value solution. So domain is all real numbers, and that is true for every single exponential function. Every exponential function has a domain of all real numbers because you can plug anything in there. Now the range has to do with that horizontal asymptote because this curve is never going to drop below, in this case, that x-axis. So the range is going to go not including 0 because the curve is never going to actually intersect the x-axis. So the lowest it will go is up to but not including 0, but it will go up forever, so our range is not including 0 through infinity. Our goal is going to be able to graph exponential functions without making a t-chart, without making this table. But to do that, the first thing we need to understand is how does changing the base number of the exponential function change the look of the graph, whether this base number here is big or small. Let's take a look at several graphs where the base numbers are different, specifically kind of big base numbers and really small base numbers. Starting off with 2 to the power of x, the one we just graphed, let's compare that to the graph of y equals 3 to the x. Notice y equals 3 to the x also looks like a J-curve, okay, but some of the similarities. They both have the same y-intercept. Any number to the 0 power equals 1, so that's why they have the same y-intercept. The only difference here is the 3 to the x skyrockets faster, and then it also gets smaller faster. So big base gets big fast and small fast. How about y equals e to the x? Now, e is a number. It is not a variable, and you're going to start seeing e a lot, especially for exponential functions and logarithms. So the base e, that is the number approximately 2.71. It is an irrational number, kind of like pi, right? Pi is 3.14 and then goes on forever. So when you see e, please do not think of it as a variable. It's just a number. Now 2.71 is bigger than 2, but smaller than 3. So what would the graph of y equals 2.71-ish to the x power look like? It's still going to look like a J-curve. It will still have the y-intercept of 0, 1, but because it is the number e is smaller than 3 but bigger than 2, it's going to skyrocket slower than base 3 but faster than base 2. And then thereafter the y-axis coming over here to the left, it's going to draw nearer and nearer to that horizontal asymptote, the x-axis, but it's going to draw nearer, slower than the base 2, but faster than base 3. Okay, what all of these have in common, they are all exponential growth functions, and that is because the base numbers are bigger than 1. So if you were going to graph y equals 10 to the x, it would still look like a J-curve going through 0, 1. It would skyrocket. It would skyrocket even faster, and it would come down even faster, but still getting close to the x-axis. So those are exponential growths, bases bigger than 1. Okay, how about if the base is a small number like 1/2? Well, what ends up happening is the J-curve, it looks like a J-curve reflected across the y-axis. Kind of think about why that would be true. 1/2 to the 0 equals 1, so it still has the same y-intercept, but if you substitute in 1, we'll get 1/2. I plug in 2, 1/2 times 1/2 is a 4th, plug in 3, and I get 1/8. So as I substitute numbers going to the right, I'm getting a smaller, smaller, smaller answer. So we're getting close to that x-axis, moving to the right. But as you substitute in negative numbers like -1, 1/2 to the -1 is 2, 1/2 to the -2 is 4, 1/2 to the -3 is 8. So as I substitute numbers moving to the left, my answers get bigger, bigger, bigger very fast. And so we kind of have that reverse J-curve. Now compared to, say, this one. Notice that base number is still really small, So it's going to be that reverse J curve. But notice that when you graph that one, it skyrockets faster than the 1 to the 1/2. Okay, but think about the numbers 1/3 versus 1/2. The number 1/3 is smaller than 1/2, yet it's skyrocketed faster. Okay, so I don't want you to take away that big base skyrockets fast. Okay, that's true if you have an exponential growth, but if your emphasis is a decay, then when you have a bigger base, it skyrockets slower. Okay, now it turns out that exponential functions, the bases have to be positive. So they can be between 0 and 1, or they can be larger than 1. We don't have any bases that are 1, because 1 times 1 times 1 times 1 is always 1, and we would just have a horizontal line. Okay, so let's go ahead and formalize the definition of an exponential function. Formalizing the definition of an exponential function, notice we have f of x is equal to a to the power of x. A represents a number to the power of x. So the variable exponent. Then the base a must be greater than 0. In other words, it's got to be positive, but it cannot be the number 1. We have two cases then that follow. The a value, knowing that it has to be positive, it might be bigger than 1, but it might also be between 0 and 1. If it is greater than 1, that base number, then it skyrockets. It represents exponential growth. But if the base number a is between 0 and 1, then it's going to be a decay model. Okay, now in both instances, the domain of every single exponential function is all real numbers, because you can substitute any number off the number line into one of these functions and you will get out a real value solution. They go forever to the left and they move forever to the right. Okay, then the range. And actually I'm going to back up just really fast there, because they grow so very fast, sometimes people will think that there is a vertical asymptote because they're skyrocketing. They continue going to the right forever, no matter what number you plug in. So there is no vertical asymptote. It's just that when you look at them on a piece of graph paper, it kind of looks like there might be a vertical asymptote because they're going up so fast. But eventually they will continue moving to the right forever. Okay, then the range, they're never going to drop below that horizontal asymptote. And for every exponential function that has not been shifted around, right, moved up, down, right, left, all that good stuff, any exponential function that has not been shifted, the x-axis is the horizontal asymptote. So it's not going to go any lower than 0. It won't reach 0, but it will go up forever. So the range is not including 0 through infinity. All of them have a y-intercept of 0, 1, because no matter what the number is to the 0 power, that equals 1. Horizontal asymptote, again, that is the x-axis. And then a review of some vocabulary. Every single exponential function happens to be 1 to 1. Okay, remember 1 to 1, couple things about 1 to 1. It passes both the horizontal line test because it's a function, but it also passes the vertical line test. Every x has a unique y and every y has a unique x, so they are all 1 to 1. Okay. Then just some other little fun vocabulary, bonus vocabulary. These functions are also called monotonic. Monotonic functions are all increasing or all decreasing. So over negative infinity to infinity, this one is going up, 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 all increasing. This one is all decreasing. Okay, so far, we have defined an exponential function, and we've graphed a few, gotten the basic shapes, J-curve or reverse J-curve, y-intercept there at 1, and horizontal asymptote, that is the x-axis. we're going to run through from here on out a review of how graphs shift based on adding, subtracting, and multiplying. I'm going to go kind of quickly because this video is going to get very long because this next part is a review. But here we go. Okay, we start off with parent function that happens to be 2 to the x. Okay, we've got that j-curve, y-intercept at 1, horizontal asymptote at the x-axis. So review, what does replacing an x with negative x do to the graph of a function? When you replace an x with a negative x, you're going to reflect the graph across the y-axis. Okay, and there is our final graph. Doing this by hand with your homework, I have a dashed line there for my parent function just so that it doesn't look like my final graph, but you can use maybe a light pencil line, and then as you continue to shift things around, light pencil lines, and then for your final graph, make it a really dark line and make sure your horizontal asymptote and y-intercept are also kind of darkened in. Okay, this one here, there's my final graph. It should look a little familiar to you because we also saw that we can get this shape when that base number is between 0 and 1. So I'll just take 2 seconds here to show you that. If I had a base number of 1/2, well, 1/2 is 2 to the negative 1. And then negative 1 raised to the x, power to a power, we multiply exponents, and it's equivalent to 2 to the power of negative x. So here, notice that base being small and having a negative exponent kind of has that same result, has that look of the reverse j-curve. Okay, here we have another one. Parent function is still 2 to the x. So there's my parent function, sketching that in lightly. But what does multiplying by negative 1 do? I went ahead and put the common mistake here, danger, danger. Okay, this does not mean negative 2 to the power of x. This means negative 1 multiplied by 2 to the power of x. Okay, so multiplying by negative 1, multiply, just a little visual reminder, multiplication symbol kind of looks like an x. Multiplying by negative 1 reflects across the x-axis. So if I reflect everything across the x-axis, there's my graph, and that is the graph of y equals negative 2 to the x. 3 times 2 to the x. Parent function will still be that j-curve 2 to the x. Okay, danger, danger. Oh, please don't do this. Okay, 3 times 2 to the x does not equal 6 to the x. Exponents before multiplication. Okay, that is simplified form. So what does multiplying a function by 3 do to the graph? Well, that is going to be a vertical stretch by a factor of 3. So all of the y-coordinates get multiplied by 3. The horizontal asymptote is there at 0, and 0 times 3 is still 0. So that does not change the horizontal asymptote. But if I come in, there's a height of 1. 2 to the first power used to be 2. 2 times 3 my bad. Height of 1, and then times 3 is 3. Here we have the function used to be at a height of 2 times 3. It would now be at 6. The height there would have been 8, but now times 3, it'd be clear up at 24, way off the graph. Okay, similarly here on the left-hand side of the y-axis, right there we'd be at a height of about 1/2. And so the height now, 1/2 times 3 is 1.5. Okay, so notice the pattern. Coming off the x-axis, we are 3 times as far off of the x-axis. Those are where our new points are. And there is a sketch of y equals 3 times 2 to the x. Okay, next, if you multiply a function by a small number between 0 and 1, the parent function is still 2 to the x, but this time multiplying by a 4th, that is going to be 1/4 as high. It's going to be a vertical compression. Just put here again, danger, danger. Do not multiply these numbers together. 1/4 times 2 is 1/2. That is not equivalent. Okay, so that is the simplified version. Okay, that times 1/4, that means that you're going to have a vertical compression. You're squishing it 1/4. But when you say it, you have a vertical compression by a factor of 4. Whatever this fraction is up here, in this case 1/4, so we said 4. If it was 3/4, we'd say by a factor of 4/3. All right, so that's not going to change the horizontal asymptote there, the x-axis. 0 times 1/4 is still 0. But that point right there, 1/4 as high. Okay, right there. If I just go to a few points, notice if I just come off the x-axis 1/4 as high as it used to be, that's going to get me a good sketch. Okay, you're just coming off the x-axis 1/4 as high as it used to be. And there is a sketch of y equals 1/4 2 to the x. So multiplying by a number between 0 and 1 is a vertical compression by a factor of the reciprocal. Okay, now here we have something that is relatively new to you. We have multiplying by 0.5, but we're not multiplying the function by 0.5. Our parent function is still 2 to the x. Okay, and there's my parent function. But that 0.5 is inside of grouping symbols. When you are up in the exponent, okay, when you're up in that exponent, anything that's in the exponent is inside of parentheses. If you try to type in to your scientific calculator or graphing calculator 2 to the power of 0.5 times 8, you want to put 0.5 times 8 in parentheses in that exponent spot. So kind of like what we've learned in the past. Remember when we added outside of parentheses, it was up. Subtracting outside of parentheses, it was down. But when we added inside of grouping symbols, it did kind of the opposite of what we thought. Adding inside of grouping symbols moved us left. So when we are inside grouping symbols, we're kind of off kilter there. It's going to be the opposite of what we think. So 0.5, which is the same thing as 1/2, we're multiplying inside grouping symbols by 1/2. It's going to do the opposite of what you think. It is not going to be a compression. It's going to be a stretch. Okay, so inside grouping symbols, multiplying by a number between 0 and 1, it's going to be a horizontal stretch. So I'm going to grab this and I'm going to stretch it. Now I think inside grouping symbols is relatively easy to remember that you're moving it this way, because think about a set of parentheses, right, moving them this way. Okay, so we're going to have a horizontal stretch by a factor of 2. Now notice the distance there, right there, currently is a distance of 1. And if I stretch it, I'm going to double the distance from that y-axis. So the new point twice as far, and it would be right there. Okay, then let's just grab another random point here on the original function. Its new point would be over here. It's going to be twice as far from the y-axis if I'm horizontally stretching it. Okay, even right there, we're at a distance of -1 from the y-axis, and if I stretch it times 2, we're going to be at a distance of -2. Okay, so then, and stretching the asymptote this way isn't going to do anything. So here we have our final graph of 2 to the power of 0.5x. So when you are multiplying x up there in the exponent inside of grouping symbols by a small number, it will be a horizontal stretch. Okay, here notice parent function is still 2 to the x. And this time we are multiplying by a kind of big number. We're multiplying by a number bigger than 1, multiplying by 3. So when we're inside grouping symbols up there in the exponent, it's going to be 3. It's the opposite of what you think, right? Times 3, you think stretch, but it's a compression. So it'll be a horizontal compression. We're going to squish it times 3. Okay, so if we had that point right there, think of it as if it is 3 times, squish, squish, squish. Okay, it's going to be a third as far off the x-axis. So the new point would be right about there. Okay, at that point, if I go a third of that distance, it's going to be right about there. Okay, so let's just make a quick sketch there. Any one of these points, a third of the way. So right here, the y-intercept was right on the y-axis, so it stayed. Okay, but right here, the distance to this point, if I go a third of the way, it's right about there, or all the way over there, a third of the way is right about there. Okay, clear over here, from the y-axis all the way to there, a third of the way is right about there. Okay, so there is my graph of y equals 2 to the power of 3x. The takeaway again, if you are multiplying inside of grouping symbols by a number bigger than 1, it is going to be a horizontal compression. Okay, now these ones I think are a little more straightforward. If you simply remember that when you're up there in exponents, you are inside of grouping symbols. So we've got our parent function 3 to the x, so it looks like a J-curve. And we're inside of grouping symbols. So when you add inside of grouping symbols, it's going to move you left. Okay, so grab that and drag it left 1, and there's my final graph. Okay, how about this one? Parent function is still 3 to the x, so you just sketch in a J-curve. Notice when I sketch in a J-curve of 3 to the x or 2 to the x, and I'm making a sketch, I'm just like, whoop, and they probably look about the same because it's a sketch. Right, there's still our parent functions. Now inside of grouping symbols, minus 1, inside of grouping symbols, it's going to take you right. Now there is an exception to right and left, and this is the danger one. If your x inside of grouping symbols was a negative x, in other words, you replaced x with a negative x, then that means you reflected the graph across the y-axis. And then, because of the negative x inside of grouping symbols, it disrupts everything else. Then all of a sudden, if there's a negative x inside of here, then plus would be right and minus would be left. Okay, but that only happens if the x inside grouping symbols is negative. So many little rules. Okay. Let's take a look here. This one, I grab that 3 to the x, I drag it right 1, and there is my graph of y equals 3 to the x. Okay, when you drag a horizontal asymptote right and left, it doesn't move it, so that part stayed the same. Okay, now notice this time minus 1 is outside. It's just off to the side. So minus 1 is going to take this function, that original parent function, that J-curve, and drag it down 1. I'm not drawing the pictures this time, but if you drag it down 1, that means that vertical asymptote also went down 1. Okay, y equals 3 to the x plus 1, outside of grouping symbols, so that would take you up 1. So I draw that basic J-curve and then drag everything up 1. Finally, let's put this together with a more challenging problem. This has got a lot going on. I tried to think of, as many tough things as possible. So starting off with that parent function, we would have a J-curve, and it would be skyrocketing, right? Horizontal asymptote is the x-axis, parent function. Okay, then we want to do things in a certain order. So quick reminder, you wake up in the morning and you stretch. Okay, you want to do your stretches first. Then Before you leave the house, you check your reflection. Make sure there's no toothpaste. So do your reflections next, x-axis, y-axis. And then you move about your day. So right, left, up, down. It doesn't matter the order you do right, left, up, down. They're just at the end. Okay, so we've got our parent function. We're looking for any stretches. Now, we would have to have in front of the 3 multiplying by a number to get a stretch. Multiplying by a big number in front of 3 would be a vertical stretch. Multiplying by a small number between 0 and 1 in front of 3 would have been a vertical compression. Okay, we don't have that. This 3 is not a stretch. It's the base number. It's a part of the parent function. Now, if I had a horizontal compression or stretch, then we would have a number up here in the exponent spot, and if the number next to x was bigger than 1, we would have a compression, horizontal compression. If the number in front of x was a small number between 0 and 1, then we would have had a horizontal stretch. We don't have any stretches. So moving on, okay, reflections. A reflection, there are 2 kinds, x-axis, y-axis. If in front of the 3 there was a negative, that would mean times -1. And if there was a negative in front, times -1 would have been a reflection across the x-axis. We do not have a negative there, but we do have a negative with the x up here in the exponent. So the x was replaced with a negative x. So that means that we're going to have a reflection across the y-axis. All right, next we're on to moves, up, down, right, left. It doesn't matter if you do up, down, and then right, left, or vice versa. I'm just going to go with right, left next. And this one is a little crazy because we're inside grouping symbols. Normally inside grouping symbols up here in the exponent, plus would move you left. But because the x is negative, it's going to move you right. Okay, so we're going to move right 4 because of that. And then lastly, that -2 on the end, the -2 on the end, outside of grouping symbols, -2 moves you down. Now, if we follow that process by just making some light sketches, which one of these or ones of these is going to affect that horizontal asymptote? We've got our parent function. Right now, the horizontal asymptote is there on the x-axis. We reflect across the y-axis, not changing it. Drag the horizontal asymptote right 4. It's going on forever to the left and right, not changing anything. And then down 2. So the only movement that is going to affect that horizontal asymptote is the down 2. Now in my picture, I went ahead and just did one at a time. The blue one, notice from the red, the original, I reflected across the y-axis, it became the blue. Then I took the blue one and moved it right 4, became the green one. Then the green one, I moved it down 2 and it became this kind of purplish one. So my final graph, moving also that horizontal asymptote down 2, my final graph is this purplish one here with the horizontal asymptote right there at -2. We should be able to answer a handful of questions. The domain of every single exponential function is all real numbers. They go forever to the left and forever to the right. There is no vertical asymptote. I know that this purple guy is skyrocketing so fast, it looks like it's getting closer and closer to something, but it is not. It's moving. This purple one is moving to the left a little bit at a time, and eventually is going to go forever to the left. It's just going to take a long time because it's skyrocketing so fast. Okay, horizontal asymptote is down there at -2, y equals -2. It is an equation, right? So y equals -2. The range, this function is never going to go below that horizontal asymptote. So that's from -2 and it'll go up forever, so through infinity. The y-intercept, now when you start shifting things around, it's a little tricky to see the y-intercept. but we can algebraically find that because to find a y-intercept, we just replaced the x with 0. So I went up into the original function and replaced the x with 0. Negative 0 plus 4 is 4. 3 to the 4th power minus 2 is 79. So the y-intercept, the coordinate is at 0, 79. Now, the x-intercept you do not have to find right now because that's going to require logarithms. So you won't need to be able to do that at this point. Wow, that was a long video. The homework assignment there's quite a few problems here, but each problem should go relatively quickly. It's just getting those rules down. So please make sure you kind of go back to that last example, kind of have that maybe on pause as you do your homework assignment, because I tried to say every rule in that last example in case you need a reminder. Okay, good luck.